All right. Well, welcome to the meeting. Hope you had a good week. Before I start, is there anything anyone would like to comment on, or any questions they'd like to ask? Okay. All right. So today, what do we, actually, I think Z had a demo he wanted to do.
Yep.
So why don't we do that now?
Okay. Is it sharing right?
Yeah, I can see the screen.
Yes.
Okay. Cool. Let's just do this.
Okay.
I don't know why it's not working for this present.
Oh, to do a presentation, yeah.
Yeah. No.
I'll just go through it, yeah.
Yeah. Okay. So for my model, let's first do an overview of the model. So the agent's Braitenberg vehicle is allowed to explore stimuli in an environment and it receives two kinds of inputs from the stimuli, odor and taste. And as a result of that, the brain development happens in the nervous system of the Braitenberg vehicle in order to associate odor with taste. And taste can induce a preference over the perceived stimuli and therefore affects its movement. And then after a period of association, the Braitenberg vehicle is able to have, say, reasonable predictions of the taste of a stimuli simply based on the odor, and then changes its movement before actually tasting the stimulus. So the neural development can be perceived in two ways. So first is the Hebbian development through the changes in the inner connections. So we can visualize it in neural network, in network X, for example, and the change of the movement. For example, in the Python library, matplot and there's like animation function, and then you can visualize change of movement. And maybe other libraries can also do this. So first, let's talk about the environment. So here are some exemplar spaces. So remember, the stimuli is multidimensional. So for say odor, there can be a lot of attributes, and taste, there can be a lot of attributes. So for each attribute, we can draw the sensibility space. So for here, it is odor sensibility space, and So if you look at it carefully, there are some red dots. They are the exact location of similar sources. And basically, the attributes, the values decay with distance. And on the right are the taste sensibility spaces. So since one can only have taste if the similar sources are touched, therefore the taste spaces are just like some circles in there, and the other parts are all empty. So that is how the stimuli are distributed in the environment. So there should be some natural relations between odor and taste. So currently I'm using this mapping I defined. That is very simple. That is, each taste attribute is the sum of two corresponding odor attributes. And probably in the future, some other rules will be defined and used in testing the model. So currently, it's just like this. So I2 is the raw gustatory attributes array, and I1 is the raw olfactory attributes array. So that is the nervous system of the Braitenberg vehicle. That is the general structure I have made so far. It's like this. In this picture I draw, the network assumes there is 10 olfactory attributes and 5 gustatory attributes. The olfactory inputs are first processed in the olfactory bulb, and then the processed information is transferred to the olfactory interneurons, and at the same time, the gustatory inputs is transferred to the gustatory interneurons. In Hebbian development, the synaptic plasticity happens among those interneurons. So I make those arrows gray, so it says the dynamic connections. And also the output of the gustatory interneurons is collected by the movement system, and the movement system controls the movement. The olfactory bulb, so that one over there, is a modified Lee-Hopfield network. So there are two types of cells: the mitral cells, which is in gray, and the granule cell, which is in black. So in the graph I made, there is 10 mitral cells and 10 granule cells. Basically, the mitral cells receive input and gives output, and so that's like the mitral cells facing to their external inputs, and the mitral cells is just like external, and granule cells is just inside. Granule cells function as inhibitors. So there are gap junctions between two mitral cells if they are close to each other. So just like this over here. And gap junctions are basically connections that has no loss in signal values. That means the weights are all 1. And mitral cells excites nearby granule cells, which is also in red, and granule cells inhibits nearby mitral cells, which is in blue. So that resembles the real mammal olfactory bulb. The dynamics of the olfactory bulb can be described as 4 differential equations. So X and Y are the internal states of mitral cells and granule cells respectively. And I is the input, which changes over time, and C is the constant input to the granule cells. And activation function F is hyperbolic, and alpha is 1 over time constant. M is the weight matrix from granule cells to mitral cells, and G is the reverse, and L is the intramitral base matrix. And all entries in these matrices are non-negative. The function gamma sets the lower triangular entries to 0. And basically, that's the general Hebbian algorithm. So the first 2 differential equation tells the changes of the internal states over time. And we can see from this that each pair of mitral cell and granule cells is an oscillator, and constant inputs granule cells ensure the stability of the oscillation. The changes in the 2 weight matrix are Hebbian, as I said, and therefore allows the olfactory bulb to adapt to the input. If the adapting rate eta is properly set, then the system is more resonantly sensitive to the input and changes in the input. So I can show 2 examples here. Can you see this tag, this figure?
Yes.
Okay. Alright, so this one is the result of the simulation where there is an Hebbian input, Hebbian development. And this one is the example, is the result of the simulation when there is no Hebbian development. They all take in the same initial input, and the initial input changes in the same manner, as you can see from here. So it's just like simple additions of different values to the initial inputs in some specified time. And when there is no Hebbian development, there is a lot of zeros, and the network tend to magnify those that are very great and tend to make those are small to be zero. And that is actually harmful when the network is associating the odor with taste. And for this one, if the ether is parabola set, then the power of signals can have a very nice pattern and then affect the association of odor and taste. Right. Sorry. And here it is the inner part. So the inner part is where the Hebbian synaptic plasticity happens. And the dynamics of the inner parts can be described in this single differential equation, where W is the weight matrix over here of these connections. Here I1 is the input to olfactory interneurons, and I2 is to gustatory. So D is the synaptic degradation matrix I defined. And I defined this because synapses are not there for free. And there is a lot of factors to cause them to degrade, such as calcium level, neurotransmitters, cell cycle, etc. So it is believed that the life of a synapse depends on the presynaptic activities that affect all those factors I just mentioned. So I took this idea and proposed this way of calculating the degradation matrix. And the degradation is reversely proportional to the presynaptic activity, which is I1. So as you can see, there's like one directional connections over there currently. It is reversely proportional to the presynaptic activities I1 times the weights, the magnitudes of the weights. And I add a depression rate over here is just make it like a smooth impact factor so that there will be no division by zero. And adding this degradation significantly lowered the errors at less static testing. That is the testing in Braitenberg vehicle without movement. It's just like input is directly feed to those Braitenberg vehicle, and Braitenberg vehicle is not moving. So here is the example when there is. So here is the example of the static testing, and it is also a comparison when there is a Hebbian development in the olfactory bulb and when there's no Hebbian development in the olfactory bulb. So the error is lowered when there is Hebbian developments in the olfactory bulb. So currently, the preferred parts in movements is not finished. And the vehicle currently is just curious, but not emotional. So my current thought about the preference parts is to apply each taste attribute and a unique preference function and sum them together. So it is as simple as that currently. And for curious parts that I've already implemented, it is just using KD tree to partition the space, and the Braitenberg vehicle will approach the nearby stimulus sources, and when there exists some unvisited stimulus sources, it will firstly approach those unvisited stimulus sources. But when all of them are visited, then it just go for the very nearby one, but it might not be the nearest. So yeah, so that is basically the description of the model, and here are uncertainties I thought about. So firstly, that is how to determine the minimum distinguishable distance between two similar sources. So firstly, I think taste receptive field should not overlap. So for example, in this part, if you look at this taste sensibility space carefully, there is overlap in the receptive field. I don't think it is acceptable in the road as well as in road chaining. But because the older spaces has attributes like the similar sources in the older spaces was like have their attributes degrade with distance. So that means the older spaces are affected by the similar decaying function and also by the number of stimuli. So what is the distinguishable distance between those two stimuli sources for as well as for the older spaces? That's currently unsure. And probably testing with different parameters can tell the answer. And also the second is the preference-based movement control. So how to control the movement based on the preference to the stimulus currently receiving. I have some general idea, but I'm currently thinking about how to implement it to make it efficient. And probably I can look at the simbrain because it already has that very nice feature. And the third one is the behavior evaluation, or say the movement evaluation. One solution I think of is to find the distribution of preferences of the stimulus of the sensory stimuli received. So after finding the distribution, if the distribution is more to the big side, then that means the vehicle is trying to make it feel good, and meaning the association learning is strong because it is the natural rule that the Braitenberg vehicle should make it feel good. And if it is the opposite, then it means the simulation, the model is not so robust. And another thought is to use this equation. So D is the distance to a stimulus source I, and C is a constant that moves the negative log function further, move the negative log function up. And the results will be large if the vehicle is nearer to the stimulus sources that make it feel good and further from those that make it feel bad. And if the resulting value is small, then the model is not robust. So currently, that is the idea I've thought of. Basically, that is my presentation today. So, any questions or suggestions?
Well, thank you, Z. That was very good. Okay, so let's see. We have one question from Jesse in the chat.
Okay.
It's about visited versus unvisited sources. Can you go over how this was distinguished by your model? Is that when the agent comes to a source, something changes and the stimuli center is checked off, essentially? Or that it would just move on after said stimulus fades out?
Oh yeah, so basically, currently I'm just using a Boolean array and to just check for the sources. So I implemented the KD tree. So KD tree is a space partitioning data structure to find the nearest neighbor. And so if it is, so KD tree, it is a tree data structure. So if the currently found stimulus source, the currently found location has been visited, then you can just go to another subtree, or go to the sibling, or go to its subtree, go to its children, if it is acceptable.
Is this a spatial partition, or is this like just? Because I think it's a spatial resolution issue, is what he's referring to. So, like, if the odor is in a certain part of the space, or if you go towards an odor or go away from an odor, is there any distinction there?
It is just a space partitioning data structure.
Okay.
So it is a two-dimensional space. Then you have x and y value, and it's like a two-dimensional binary tree. So firstly, branch using the x value, and then branch using y value, and then branch using x value, and go on. And yeah, if you want to find the nearest neighbor, just go down the tree and backtrack. And if the location has been visited, then you may just go to another children, and that's it. And just to check or backtrack.
And so then that would be at every step, like it would update as you move around the space, or
yeah.
Okay.
Yeah, there is a Boolean array. So if the location has been visited, then it just set to true. So that is currently what I implemented.
Okay.
Thank you.
How about Stefan? Do you have any questions?
Yeah.
Okay.
It was interesting for me to see what is a space distance function, like the space visualization that is shown in the very beginning of the presentation. Could you go back to it, please?
Yeah, sure.
I mean, could you maybe show it to us, just to look at it once again?
Yeah, that's fine.
Yeah. Okay, yeah, that's fine. Exactly. So first, I was wondering, like you said, you calculate an effect on distance, right? So this, like these two maps, it's not really clear why the right map has just small blurs, and whereas the first map has like the one on the left side. It has kind of.
Sorry. I actually didn't mention that. So the odor attributes decay with distance, but for taste, we have taste when we contact the thing, right?
Okay.
So, yeah. So it's just like only within some very, very small distance you have taste. So that's like only just some dots.
Okay. Mm-hmm. Yeah.
It's all empty.
Makes sense. Makes total sense. And so, it's just interesting. I was implementing basically the same in my simulation. Which decay function did you pick for your order sensibility, or like for your order function?
Yeah, I can actually show you the code.
Okay.
And open. It's okay. So I'm using this here.
Okay.
Yeah, it is just like
just an exponential.
Yeah, exponential.
Uh-huh.
I didn't use linear because first I think exponential make more sense to the real life, and using the exponential can make the border clearer. I think using linear is going to be more challenging.
Yeah, that could be actually. Okay, and the second question is about degradation that you mentioned. So you kind of mentioned that you're updating weights, somehow degrading the neutrons, or could you explain how does it make sense in the context of simulation of the real world? Like, is it something that happens in real synapses, or just don't know?
There's a lot of factors that can cause the synaptic weights to degrade or even die. So one thing that is very commonly understood is long-term depression, but long-term depression is more complicated. So long-term depression can due to it is like there's a lot of factors cause the long-term depression, but for a cell, so neuron is a cell. So for a cell, its life cycle is affected by something like calcium level, like the natural the cycle the cycling of enzymes. Some factor like this. So the firing will cause the changes in the calcium level, and I have read some papers, and it shows that if there's like more synaptic if there's like more presynaptic activities, then the synapse will gonna be maintained. And if there's like less presynaptic plasticity, then the synapse would degrade, but in very slow, maybe in very slow speed. I'm currently not sure about speed, but there's a lot of factors causing this. I'm doing this because I think just Hebbian is not enough, and because my simulation contains a lot of noises, because it is like simulating, just like letting the Braitenberg vehicle to run in the environment, and there's a lot of noises, and it's like learning. So like running. You go toward this and you learn, and go toward this and learn. So yeah, the samples for learning is very noisy. So I'd say the degradation matrix is what I currently use instead of like a very complex noise filtering technique. But I'm currently not implementing very complex noise filtering technique and I don't know how to actually. So I'm using the degradation function. So to make the noise, not affect the Hebbian learning so much.
And what do you refer to as noise in your model in the context?
Sorry.
What is noise in the context of your model?
Oh yeah. So
how do you distinguish between signal and noise? That question.
Okay. So for example, very say typical machine learning, you just like feed samples and samples and samples. But for this simulation, you are running in environments of a lot of samples, and you are learning in the environments of a lot of samples instead of just learn from this sample and then change to another sample. So there's a lot of environmental noises. So that is the noise. And so firstly, the olfactory bulb has some functionalities in filtering the noise. And so it basically turns the raw attributes into oscillations. And when you are moving, if some attributes is like increasing over time and some attributes is like decreasing over time, right? So if it is like increasing over time, then the oscillation will change. And if like decreasing over time, then the oscillation will change. So if we look at it, if we do not look at this term LFX, then a pair of mitral cell and granule cell is like a damped oscillator. But when they are connected together, it's going to be more complex. But a pair of mitral and granule cell is a damped oscillator, and when when the impulse is like changing, impulse is like say increasing, then oscillation will go on. And when it's like the impulse is like decreasing, then oscillation will become will go away very soon. So yeah, look at the figure. So you can see very clearly from this figure. I set the inputs to change at time 20, 50, and 100. Yeah, T changing is this. And changing value is like this. So for mitral cells 8, so it's just like as time 20, 50, and 100, it's increased by 0.6, which is very large because I is generated between 0 and 1. So you can see very clear increase of magnitude, and therefore a very clear increase in the power of signal. And for this one, it's also very clear. So it's like decrease as in 50, very clear, and in 100, and then go to 0, oscillation. And also another reason I use Hebbian development in the olfactory bulb is because, so for this sort of sub-threshold, I set threshold to 1. And for this sub-threshold oscillation, you can't really tell what caused it to oscillate. So for mitral cell 7, there is actually no change in it over time. So why is like a change in at time 50? So that means it's probably affected significantly by its surrounding cell like this. So when there is Hebbian development in olfactory bulb, it becomes at least more reasonable. Yeah. Did that answer your question?
Yeah. Okay. Thank you.
Actually, I have a couple questions. So, first of all, the olfactory bulb. Is there any significance to the topology, or is it just the way you organized it on the page? I mean, the circular. So the circular nature of the olfactory bulb network. Is there topological significance to that? Is it?
Yes.
Yeah.
Yes. So olfactory bulb is just like a elliptical ball.
Yeah.
And mitral cell is a cell that receives before mitral cells, there are some other cells to classify the odors. So there are a lot of receptors, and then receptors are classified into a class of cell. And say in this class of cell, each cell is responsible for one type of odorant, and then the input. So that is treated as the attributes of the input. So I didn't implement that class of cell because it is just like classifying. It is very simple. So and then each cell synapse to a mitral cell. And olfactory bulb is just like in the outer sphere, there's a lot of mitral cells, and in very inner parts, there's a lot of granule cells. And the basically structure is like this. So mitral cells has gap connections with each other. So these two Y-shape are mitral cells, and granule cells are just like inhibitors. And this little over there input to the granule cell is the central input to the granule cell, IC.
Okay.
Yeah, that is basically mimicking the real olfactory bulb.
Yeah. Yeah. Okay. Yeah, that's good for now. I have a couple other questions, but I can't really figure out what they are right now about this. But so the next part I wanted to talk about is noise, signal and noise. So you said that you don't want to filter noise, which is true. You don't want to filter noise, and the reason is because noise can be actually good for the nervous system, in a way that we don't really understand fully. So, like in a typical, like you said, in a typical machine learning application, you'd be very interested in minimizing noise. We just had a talk about that in my other group yesterday. How do you like? In that case, it was there. We were talking about deep learning, where they have layers of neurons, and as it turns out, like a lot of these deep learning models, where they keep adding layers, it actually improves accuracy, but it actually adds some sort of residual noise to the model. And in this case, that residual noise is bad. So they had to find ways to get around it. But in the nervous system, there people have studied noise as a good thing. Like, for example, stochastic resonance and things like that. So, that's something that you don't necessarily want to filter, or you want to, you don't want to just say that's bad, that's all bad. So, I think that's good that you're just kind of going with the noise, see, where it leads you. So, yeah, I think that's good. I think, yeah, a lot of this stuff is really good. So, my understanding of your structure is you're going sort of the odor, and then you're going to the movement model, and then you're going to the taste model. Is that correct? Like a sequence of so first of all, the thing senses an odor, and then it moves, and then it tastes. Is that correct?
Yes, but the taste and the odor are coming simultaneously.
Okay.
Yeah. And it's just like the Hebbian take the activities of this, and then exchange the weight from olfactory interneurons to gustatory interneurons. And when there is no taste input, so when there is no this, sorry, when there's like no taste input, then it happens. Then just it's going to the olfactory interneurons will just like create some valves in the interneurons, and then that will become that's what becomes the inputs to the movement system.
Okay. I see. So the movement system is sort of a secondary system. You're giving it information, and it's moving just based on that.
Yeah.
All right. Yeah, that's yeah.
I didn't find a proper model for gustatory inputs. I actually did, but that is the cell model. That is the modeling on the calcium channel and stuff like this. It is very hard to implement it in a network model. I did find papers about how the gustatory system works, and it is believed that there is like a gustatory map in the brain. So I guess this actually starts from the map. So it's not from the taste. It's not from the chemicals. So the input is actually, I would say the input is, it is the activities in the brain.
Yeah.
It is the activities of the maps, the taste map in the brain.
Right.
It is not the chemicals.
Yeah, I think that's probably, it's probably I don't think there is any sort of network model. At least people haven't come up with one. So that's usually the way people, they map like different tastes. I think they're actually like, in humans, there are like 6 or 7 tastes that they think are innate, and then you have like, you combine them or something like that. But it's not really a network model in the sense of, something we can validate. So I think you're on the right track with a lot of this. So this is all kind of, some of it's been implemented, some of it's been not, correct? Like, which parts have been implemented so far?
I have already implemented all of them, except the movement system.
Okay. Well, that's pretty good.
Okay. But I think if I wanted to create an animation, I don't know if it's gonna be taking a lot of time. I don't know.
Yeah.
If it did, then I probably should think about Python or other faster languages.
Yeah. Well, I would focus on just getting everything implemented first. I mean, without doing the animations, I mean that's secondary. But and so Stefan, of course, knows pretty a lot about simbrain now. So he might be able to I don't know if we want to share resources on that or what, like we talked about in prior meetings, but. It would be good to have, if you guys want to talk on Slack or something about, if you have a problem or something, he might be able to help you.
Yeah, that'd be awesome.
Okay.
Yeah, sure, we can try that.
An expert in simbrain.
Well, thanks a lot for that. Yeah.
And I just thought of one thing.
Okay.
One more thing. When I read a paper, I read a very interesting paper in that there are two kinds of gustatory receptor cells. One is like specialist, so they are only sensitive to one type of taste, and another is like a generalist, so they fire. So say some fires when it encounters 3 kind of taste. Do you think that is good for this model? If I implement it in this model, I don't know, but the function of the generalist is not clear right now.
Yeah. I don't know.
Okay.
I'd probably stick with what you have and see, because this is a lot already. It's just you don't want to.
Yeah.
So I mean, it was like when I don't know if you guys have ever heard of I guess grid cells. Have you ever heard of grid cells? It won a Nobel Prize recently. So when that paper first came out, people were talking about modeling that in a group I was in, and it was it was actually pretty premature to really get a handle on the modeling. I mean, since then they've done a lot of experimental work on it, but sometimes when there's a paper where just they find some new phenomenon, it's very hard to turn that into modeling for a number of reasons. But I mean, that's just something I thought I'd mention but I think what you have here is looks like it's pretty well backed up by the literature. Do you have a literature review for a lot of this stuff?
Of the generalist and specialist?
Yeah, well, I mean, a lot of the stuff that you reference in here, a lot of the information you're working off of, or I guess they're based on papers in the literature.
I think that
Yeah, I mean, we should assemble that actually into like a list, like a yeah. So like have like a document where we have them all sort of cited and with some notes. That would help. Yeah, that would help.
Yep.
Okay. Okay, so Jesse, you had any other questions?
No, but this is a really interesting presentation, and I think I'll have a lot to think about and probably talk up later about it. But that's all for me.
Yeah, that's good. Yeah. So yeah, if you have anyone has any questions that follow up on that, ask them in Slack or at next meeting or whatever. So thank you again, Z. So why don't we move to the board real quick? Let's see. We can have this. All right. We'll go to the board here. Let me put the repository link in the chat. And if we go to the repository, we go to projects, we go to group meetings review, and then we can see that we have a very big, very full board, and we have a lot of things that are done, which is good. We have a lot of things in progress, and then to do. So the in progress, number 24, this is for Stefan. I did actually follow up on the conference funding through professional organizations, and I forgot that there's a travel grants link or travel grants list at this link in the issue. So if you open up the issue, you'll see there's a link there, and there might be some interesting stuff in there to apply for. It's just like different professional organizations and things like that. They might be able to offer like travel grants and smaller grants that you can apply to. They're varying deadlines, but I thought I'd point that out.
Oh yeah, thank you.
Okay. Yeah. Number 4, share resources and implementation ideas. So this is again, we just talked about this. So Simbrain might be an example of this, where we do some sharing here. We put a note in here. And there we go. Put the note in. And then, okay, that was number 4. The number 18 is create Trello board with tasks. So that was something that Stefan created, and I've kind of been going through and actually putting some of those cards into issues on this board. So, but I mean, there are a couple things that I put over, but I check it periodically. Is there anything I should be aware of on that board that you have recently updated?
Not really, no. I guess I've solved all the issues, by the way, that are in progress.
Okay. Yeah. So, let's see. Find data set references for GitHub repository. I am working on that. Actually, there was a recent paper, I think this last week, that came out on the C. elegans connectome. They did another pass at it, and they have a new version. So I can post some of that information up on in the repo if people are interested in looking at it. C. elegans, of course, is the organism that has a 302 neuron connectome. So we know all the connections, or they map these connections based on gap junctions and electrical activity. So they're really kind of estimating it, but it's small enough so that you can actually do that. And so that'll be interesting. Number 23, visualization of networks. I think we were talking about that. So if you have any, I think at this point, we're kind of still thinking about how to do that. And I think I mentioned at the last meeting, that there are different open source Java and Python. I didn't provide the options for this, but I'll do that soon here. I just kind of slipped my mind. But yeah, we'll keep working on that. But that's something that we can do. That's kind of down the road, I guess. A couple more weeks, we can get into that. Work on binary encoding. So that was, I think, Stefan was. I kind of assigned it to everyone, but I think Stefan can update on that.
Yes, as said, I've implemented the binary encoding for adjacency matrices, and I've defined grammar encoding to be the second step, which I will do when we have enough time, which I feel we won't have.
Okay.
Basically, to be honest, because there is some more stuff to be done with the guided user interface itself.
Okay.
But still, well, maybe if it comes to it, I would do grammar encoding, and the binary encoding of adjacency matrices, it's pretty much done now. So
Okay.
I'm finished with that.
So why don't we put that over and done?
Yeah, we can do it.
Okay, and then maybe we'll put work on grammar encoding and leave it in to do.
Mm-hmm.
And then over to issue, and then we'll assign it.
So what is a grammar encoding?
Oh yeah, grammar encoding is a kind of a thing which we, do you know regular languages? This kind of piece of informatics.
Oh yeah,
Exactly. So this.
Mm-hmm.
Have you said yes or somebody else?
I'm not sure.
Okay, whatever. So just the, I don't know how it's called in English, by the way. Let's just look it up quickly. For regular language, we kind of define a set of grammar rules.
Oh, do you mean like English?
Language, yeah.
Yeah, that sort of regular language.
Regular language, yeah. Yeah, it's called regular language in English as well. So we define some kind of rules, some kind of patterns, by the way, yeah, and most of the things that we define, they are recursive, as you may know. So we kind of have, let's say we have the rule A, and rule A consists of either B or C, and C or C separately, let's say so. And then we come to the rule C, and rule C gives us maybe some end product, or maybe some other layer of recursion. So it will give us D, and D will give us something else. Yeah, and so that's the idea of grammar encoding of the graphs. So in grammar encoding of the graphs, you kind of have the first rule S, which corresponds to just the beginning of this recursion, and then you may have like some various combinations of matrices with rules. So you can have a matrix of A, B, C, D, and then kind of each of these elements of this matrix, for instance, C would encode to 1, 0, 1, 1, and D would encode to 0, 1, 0, 0. And so you kind of combine your big matrix, your big adjacency matrix, basically, from these small grammar pieces.
Okay.
I can show you maybe the illustration from the paper. It's really nice. It explains pretty much anything, I guess.
Yeah.
As that, I would use it basically for the purpose of scalability. So, for instance, if we would to simulate the connectome of even C elegans, which has 300 nodes, you can imagine that the overhead of standard approach of just straight adjacency matrix would be like 300 to square, and maybe grammar encoding will kind of save us some space, and maybe also will be more efficient in walking this random space.
That's awesome.
Yeah.
Yeah, it sounds good. Okay, so why don't we finish up the board here? So I put grammar encoding as an issue. Then why don't we go down to this one here? discuss or review components of model. So I think Ziyi did that. We'll put that in done. That was today. Thank you, Ziyi. Let's see. Community evaluation for Stefan. That's something that maybe is more down the road, or maybe do you want to do something like what Ziyi did today, where you present sort of the current state of your?
Yeah, sure.
Okay, you want to do that next week?
Yeah.
Okay. Well, I'll
Let's
put
do
you
it.
on for that, and then I'll move that over to in progress. And just be like what Ziyi did, where you just go through. I mean, you can structure it any way you want, but just I wanted to see if people had feedback for you. It's good to have air a lot of the things that are going on and your current conception of the model to get feedback. So, okay.
Yeah, I would be glad to do a presentation next week.
Okay. And then we have develop ways to evaluate movement cues generated by network. And that was, I think, what Ziyi was getting at with the thing that he's working on implementing right now. So we'll keep that. Maybe we'll put that in progress. And then we'll see how far that goes for the next couple weeks. Find means to represent sparse matrices with no compression. So this was for Stefan, and this is something I think I sent you a email about with some ideas. I didn't really find much that was. I mean, there were a couple things I mentioned, but
Yeah, sure. I've looked at it.
yeah.
Thank you very much that you sent it. I'm aware of it now.
Okay. Yeah, I don't know. I don't have a clear answer for you. But yeah. Okay, I guess we'll keep thinking about it.
Yeah, sure.
Yeah, put it in progress as well. And then create a list of visualization tools and solutions. So that's something that needs to be done, I think, by me. And then defining fitness function in context of behavior. I think that's just kind of in sort of to do still. And then discuss relevant scientific questions. So I think we talked about that last week. And again, that just means that if you can think of good questions to ask about what we're doing, or something that might be something that we might answer with what we're doing here, bring it up in the meeting or bring it up on Slack and we'll discuss it. I think it's a good exercise just to kind of get out of the headspace of just technical implementation and think about what this is all useful for. So, any other issues to put on the board before we go?
Not on my side, no.
Okay. How about Z?
Nope.
Okay. Jesse, you have anything?
Not at the moment, but I will have more things.
Okay.
For sure.
Well, that sounds good. Well, thanks for attending, everyone. And again, if you have any questions over the course of the week, we can communicate on Slack or email or whatever. And, if you don't have any questions, then talk to you next week.
All right, thank you.
Okay, thanks. Have a good week.
Take care.
Have a good week as well.
Take care.